Okay. Second. Okay. So last time we ended with a little bit of discussion of the slot line. We spent, of course, most of the time looking at the CPW and the particular problem we were having in designing that. And it sort of naturally led into this coupled microstrip line and similarly to coupled strip line. So the difference between these two is exactly the same as the difference between the strip line and the microstrip. So now you have two sort of center conductors in both cases, and microstrip doesn't have a dielectric on the top as opposed to a strip line, which has a dielectric and a ground line. So this is the symmetric one. So these structures are actually used for some very common devices, one of which I will briefly introduce today, and then one of them might actually also be the device one of you will design as part of the course project. So which I will hopefully tell you tomorrow the devices, and we will only very briefly discuss them in class, all the three devices for the three of you, and the rest you will have to sort of figure out from the book and then design. And of course, I will help with answering any doubts and things like that. But you will then spend some time understanding it and then designing a working device. So the coupled microstrip line and coupled strip line also will allow me to introduce you to slightly different types of measurements, because now there are two ports sort of involved in each side of this structure. You know, this is a microstrip. There was one port on one side and another port on other side. But now with a coupled strip line or a coupled microstrip line, you're going to have two ports on either side. So how does one characterize such a structure? What kind of measurements one can do? Some of these measurements are which are possible in microwave office, which is a simulator, are not exactly possible in a real instrument, and I'll sort of hint at how, but there are ways to convert them from one to the other. Okay. So just to remind you, we had discussed this yesterday. The moment you now have two conductors instead of one, so we have the situation where the thing is, you know, ground potential, which we assume to be 0, and then you have, say, V1 and V2 for the two conductors. And one could describe the whole thing in terms of V1 and V2, or one could describe them in terms of sort of the more natural combinations. This is very similar to how we think about normal modes. You know, if you have a two mass spring system, then you have two positions, x1 and x2, but you know, it's more natural to describe them in terms of some sums and differences, which is sort of the common mode and the differential mode of the oscillation. So it's very similar to that, because those are independent of each other. So if one is talking about the even or the odd mode, which is the case here, you can see these things mentioned here in the bottom. It is possible to excite only the even mode and not the odd mode, and vice versa. But it is not possible to excite only V1 or conductor 1 and not conductor 2. Okay, so that's sort of will make this connection between the normal modes, right? So, so we'll see how these things now come about. So let's set up our standard enclosure setting, 762. Thickness here, we can go back to 35 microns because these are going to be big structures. And width. So if you remember that for 50 ohm microstrip line, you needed something which was about 1,000 or 1,100. So we'll just start with something close to that. Let's say it's 1,000. Both of them are 1,000. And start with something, say, quite big, 500 microns. Okay. Now, it should be obvious to you that if this gap was very large, okay, compared to the other dimensions, which is the width and the height, then it just looks like two independent microstrip lines, right? Essentially, if these two are far away from each other, then there is no reason to believe that they will actually interact. So it just looks like two separate microstrip lines, which we are considering together for whatever reason. And such situations also do exist. And I'll give you an example, one case. So the question then is, how does one think about the even and the odd mode impedance which comes out? So it'll get clear in just a second. Let me just put some standard numbers here. Okay. So I have selected even mode right now. So the even mode is, as I said, the mode which is related to the sum of the two, V1 plus V2 sort of. And that's also the mode which is the one where the two are, in some sense, you can think of them as working together or independently because they're doing the same thing. Okay. So this impedance here is coming out as about 60 ohms for that. And remember, we had chosen similar numbers. Actually, let's just look at what happens to the microstrip for a similar setting. Okay, so if we put 1,000, 3235. Okay, so 1,000 was about 52 ohms. Electric constant 6. Yeah. And the coupled microstrip line, I don't know why it resets the height to 50 all the time. So it gives me something like 60 ohms. Now here there is a convention issue also, which I'm suddenly remembering. I'll just check that. Let's see if it will allow me to calculate for a much bigger gap. Oh yeah, it does. So you see what's happening is as one increases the gap, this even mode impedance is just going to what we had for the single microstrip, right? This is what I was trying to just tell you. However, if I bring it closer, then it starts to change. Now, why it's 60 ohms? Why does it go up? We will come to that in just a second. The reason I'm saying is that you would have sort of expected that as they are brought closer, maybe the capacitance would increase, and that typically causes the impedance to go up. But here it's go down. But here it's going up. But this is basically now the even and the odd modes are mixing. So that's why this thing. But I also need to check one more thing about microwave office's convention about defining these impedances. There's a factor of 2 which shows up, which will sort of conflict with the intuition when you start setting up the measurement. Okay, so yeah, so this is 60 ohms. Let's look at the odd mode now, and something like 41 ohms for this particular case. Okay, the other thing which I had pointed out to you, and this was again with respect to the microstrip structure, is that the phase constant is different for the even and the odd mode. And this is essentially connected to the speed of propagation of that particular mode. So for the odd mode, you have a phase thing of one. Let's just go to some more read. Go to degrees per micron or degrees per millimeter. Okay, 14 degrees per millimeter, effective dielectric constant of 3.79. Whereas for this even mode, it's 15.7 and 4.76. So this is larger than this one. So if the phase constant is larger for the even mode as opposed to the odd mode, then which one has a faster speed of propagation? Joydeep?
Yeah, so I think the phase velocity is the derivative of this phase constant. So for the even mode, I think it will be fast.
So the even mode is faster. Okay. What about the others? Jay?
I would guess even mode as well.
Okay. Shrujita?
Yes, even mode.
Okay. So Joydeep said that he thinks this phase constant is basically the derivative of the phase velocity. And since I asked which one has higher velocity, he's going with the value for the higher phase constant here. Any other ways one could explain this?
Can we look at the effective dielectric constant?
Mm-hmm. Yeah, so it's 4.7 and 3.79 for the odd mode.
Odd mode is faster than. No? Yeah.
Why?
I'm looking at the dielectric constant because yes, it is a derivative if we want to get the phase velocity. So I thought I may be looking at the dielectric constant to get a better idea of which has a high velocity.
Mm-hmm. So odd mode has lower dielectric constant than the even mode. So what does that mean?
Odd mode will have a higher velocity.
Exactly, because the smaller dielectric constant, your speed of light in a medium is 1 over epsilon mu, right? So it goes inversely as the dielectric constant. And you can also see that from the electrical length, which of course is the same information as the phase degree. Faster speed actually doesn't mean that the phase accumulates faster. In fact, means it accumulates slower with length. Remember that this is phase constant is per unit length. Okay. So if it's going slower, then the phase actually accumulates more in a given length. So if you had two different sections of two different pieces of transmission line of the same length, one where the propagation speed is higher than the other, then the higher one will actually have less phase accumulation with respect to the length because it's moving faster. Remember, it's the connection between the phases related to the time period and the frequency, and the speed of propagation is related to the connected with the wavelength of how fast it's going to cover the difference. So essentially what it means is that if you have a given length, the faster wave will cover that in a smaller time period, delta t, time difference. And this phase constant is omega into frequency is the same. So shorter the time, smaller the phase accumulation, and hence less phase constant. Okay. So basically the even mode is slower, the odd mode is faster. But if one stares at this, could one have guessed that? So Priyo?
Even mode.
I mean, if from the structure of this thing,
Huh.
could one have guessed this result?
You are saying that which one will have a lower effective dielectric constant?
Yeah, well, that is basically what leads to the rest of the stuff, right? So
Yeah.
why does odd mode have a lower effective dielectric constant than the even mode?
So in the odd mode, I think the vacuum part will like field lines will be there in the vacuum part, and like the distribution in the vacuum part, and inside the material will be like more part will be there in the vacuum compared to the even mode.
Yes, exactly. Because see, even mode,
Yeah.
you're going to have field lines sort of like this. I mean, again, I'm drawing a very cartoonish picture here.
Mm.
Whereas the odd modes are going to have things like this, right?
Yeah.
So more is going to be present in the air or the vacuum. So the effective quality constant is smaller. Okay. So because of that, in this case, the speed is different from for the two modes. And this actually is, as I think said many times before, is connected to this fact that the microstrip is sort of a quasi-T, and this also affects the properties of some devices if one makes coupled microstrip lines instead of coupled strip lines. So in the coupled strip line, this problem will not happen. Even the odd mode impedances will be the same. Even an odd mode phase dielectric constant, the phase constants will be the same. So we can just check that. Let's put the same values. What did I use here? 500. So the effective dielectric constant is exactly 6, which is because there is the only one dielectric constant there. So the phase constant is, of course, this is now very low impedance because there is ground on both sides. So it's coming out to be something like 20 ohms. So this will not be a very typical design if one is choosing something close to 50 ohms. Okay, even an odd mode impedances are similar, but that has nothing to do with this property. That has got to do with the dimensions of the strip and the gap as well. Okay, so let's come back to this, and now let's try to make this here. So 62 is close enough for this. So I will check the enclosure. 762,000. This looks fine. Okay, so now these kind of coupled microstrip lines or strip lines have usually separate ports for each of the structures, even though what exactly they mean now is slightly confusing. So we will come to that. And what I mean by that is that these ports are 50 ohms by definition, and how we measure the properties in this normal mode frame is what we're going to see that. So we're going to put 4 ports. And let's see. So even mode impedance was about 60 ohms. The odd mode was 41 ohms. Okay. Delete these unnecessary graphs here. So if one wants to really know the properties of these things as sort of given here, one cannot really measure S parameters of, say, 1 to 3 or 2 to 4. One can set up a measurement, but that will not tell us the necessary information. Okay. So there is something, a measurement of the right type here, and this is the one I was talking about, that you cannot really do this in using a real instrument like the vector network analyzer. You go to linear, and then you choose this G even and G odd. Okay, and the description is given here. It's even mode gamma. So it's gamma, it's a reflection coefficient, and the odd mode gamma. So this automatically sets up the right kind of excitation and the measurement. And because this by definition requires 2 ports, it gives you the choice to select 2 ports. Even though you're measuring a single port quantity from one side, you have to set up which 2 ports are you talking about, right? So that would be 1 and 2. And let's look at the magnitude dB of that. Right? I haven't played with these measurements in a while. So it'll be interesting to see. It's a setup from 1 to 10 gigahertz. You have a graph. Disable the EM structure. So I'm just going to cancel this and just double check if the resolution was too high. We were using 10 microns before, right? We were using 50 microns. Let's look at the mesh. Doesn't look that bad.
I think we changed it from 50 to 10 when we added that small structure in between the microstrip.
Yeah, but we also noticed that it doesn't. Just checking if this. Yes, we could try to. $50 should be fine for the spacings we are using. Okay. Much better. So this is, remember, this is gamma. So it's a reflection coefficient of this port 1 and 2 and plotted in dB magnitude. So it's power loss in dB, power absorption in dB. So we know that something below minus 20 is decent. So it's not, very good here, but that's understandable because it's not really a 50 ohm system for the odd mode impedance right now. According to this, it's 60 ohms. So let's see if we can do that same trick with using this as a sub-circuit. So now you see the sub-circuit now has 4 ports as expected because it's a 4-port device. Sadly, the way it numbers, it doesn't reflect the symmetry here. So 1 and 2 are on the same side, but here 1 and 2 are on the opposite side. That's okay. We just put the ports the same way. And I'm going to define just to duplicate the measurement and put it on schematic. So right now they're identical. Now if I change this thing here, so we see that it starts to get better and better, and right around the 60 ohms, it starts to turn around. And this is what we had, approximately 60 ohms was the even mode impedance. Okay, so how does one actually think about what this measurement is doing? It's so when we are setting up an even mode gamma measurement like this, what it's actually doing is it's sending an excitation simultaneously to both 1 and 2 and in phase. This phase relationship is now very important, because otherwise this V1 plus V2 and V1 minus V2 completely lose their meaning, because it has nothing if there's no phase relationship. So what I mean to say is that V1 and V2 are not now independent signals anymore, right? They're coming from, in some sense, they're coming from the same source. So I'll show you just a little bit how one can set this measurement up using a single port setup, but connected to two ports like this. Okay, so this now makes sense that this is the even mode impedance as we have seen here, and that's where you get the smallest reflection coefficient here. Okay, it won't exactly match because of the, I just told you, the calculations are done very differently, but that's close enough for this to be correct. Now let's look at the G odd. Okay, so this is the same measurement. Now it's odd mode gamma. This now sets up opposite voltages on the two ports with respect to which it is measuring. And also, and sorry, I forgot to mention that even the collected signal is looked at in a particular way. Now, ideally speaking, that's not a problem here, because if you are exciting an even mode sort of signal, then only the even mode signal will be present. You're not going to get a mixture of both. So the returned signal will also be essentially even mode. Not always necessary, because if the other time the boundary condition on the other side is not symmetric, in the sense that it maintains the symmetry of the even or the odd mode, you can actually get mode conversion happening. Okay, but I mean, exactly how Microwave Office does it internally, I'm not really sure, but I'll explain to you what it means to have this different symmetry. Okay, so let's change both of them to odd. And the, wait a second, which one is which? So, okay, blue was the one directly from the microwave structure, this EM structure, and the pink is from the schematic. So now the pink is looking much worse. Just make sure it's set up correctly. G odd. Okay. So it's showing a small value around 40 ohms, which is what we had seen here. The odd mode impedance is about 41 ohms. Okay. So again, we have used this trick of setting up the port impedances. So right now, the way it is set up is that all the ports are having the same impedance here. Okay, this is again necessary to keep everything balanced. Otherwise, this structure is slightly tricky to sort of set up for measurement. Even though the particular device we are going to be, which is going to use this coupled microstrip, there these issues don't exist because the ports are all 50 ohms anyway. But for that, a special choice of odd mode and even mode impedances have to be chosen, so that you don't get too many reflections. That's the part you guys have to explore from the book. So, right. Okay. So this is clear. Now I'm going to show you an alternate way of setting up this measurement. And that will sort of give you a slightly different picture, but a clearer picture maybe of what actually is going on in this measurement. Okay, but maybe let me pause here and see if this is slightly confusing. So, are there any questions?
So I think you mentioned this, but what you're measuring is also some sort of like a simultaneous measurement of on the two ports.
That's right.
And then maybe an addition of or something like that.
Well, the different technique I'm just going to describe next will make it a little clearer on what is happening. The only slightly uncomfortable aspect about this second technique is that it introduces another device which we haven't formally studied, and that is also a 4-port device. But it's a slightly simpler 4-port device, so at least you can understand what the purpose of the device is. But that's one of the other 4-port devices which might be one of the things you will be looking to more detail. But yes, when I define in Microwave Office to measure gamma odd or gamma even, it's a special kind of excitation and a special kind of measurement, which is happening simultaneously on 2 ports at the same time. So one thing we can actually check here right away is that does this so we have been measuring with respect to port 1 and 2. We haven't really said anything about what is happening at port 3 and 4, except that they're connected to ports of the same impedance. But if I, in the schematic where the sub-circuit, if I disconnect it here, which basically means that I have left this open, right? Does that change the response? The answer is absolutely yes. Right? So this blue is the EM structure one. Let me just, oops, wrong one. Disable that. Maybe let it be. But essentially what you're seeing is 0 dB reflection, which means unity reflection. Why is that? Well, because you are essentially launching a signal here, but on the other end, there is nothing to absorb it. So it just reflects back completely and then comes back into your input ports. Right? So that's why the reflection coefficient is basically 1. There are some small variations here. You know, you saw that when I disabled this thing, there were some little weird variations. In fact, there is already a problem here. And this is now actually is a good place to point out some of the idiosyncrasies of finite element simulation softwares. Can someone tell me what the problem with this curve is? Jay? Hello?
Yeah. Well, there is some sort of resonant structure, but why is that a problem?
First, look at the scale here.
Oh.
Maybe let me get rid of dB and look at it in linear units so that it's a lot more familiar to you.
Oh, the magnitude is positive, right? So, I mean, it's more than 1.
And?
So you're getting...
No, what end? So what is magnitude greater than 1 implies what?
So you're getting more signal than you're giving in some way.
Yeah, so that is not possible because this magnitude or greater than 1 only happens if you have an amplifier. Okay, right. This is a perfectly passive circuit. So there's no business of any gamma being greater than 1. So this is basically due to some numerical inaccuracies in the computation that you can get things like that. Let's look at the even mode reflection coefficient here. And yeah, this one also has slightly greater than 1 here. Okay, so these are things which can sometimes happen with numerical solvers because they make some approximation somewhere and some rounding error or something, and then that gives rise to these unphysical situations. The signals being smaller than 1 is also unexpected. It's not unphysical, because everything here is supposed to be, perfect conductor and lossless. I forget if the dielectric is made a little lossy or not, but the fact that there is a frequency dependence, sort of odd, is that you can have even an odd mode converting into each other, and that can definitely give rise to less power coming back on the even mode, because some power is going to the odd mode. So you can really just relabel the even mode as port A and odd mode as port B. And you're basically saying that, well, I'm measuring reflection on port A and signal went in, but some of it went to port B. So the power which came back to port A is less than what it was sent before. So if you could measure the transmission from port A to port B, where A is even mode and B is odd mode. Okay, these are all sort of, virtual ports. They're not real ports here. They're different modes. But you could see that mode conversion, then you'll see the power is going. But you can never get, greater than 1. So that is because of a numerical error in this calculation. Okay, so the boundary conditions again are very important. So I'm going to duplicate this. And now I'm going to see what's the best way to do it. Okay, I guess I will start with I'm going to have only 2 ports, and actually not even 2 ports, actually just 1 port. I'm going to put a termination on the 3 and the 4, which is the one on the other side. I could have used a port for that, but just using this. And let me Z load. Okay. So I've just terminated 3 and 4, just like we had before. Earlier, the termination was coming from the ports itself. So I've just now put I don't want to call it a port, so just put a load there. But for 1 and 2, instead of having 2 separate ports and how we did it before, I'm going to use a device which is a 4-port device, which is called 180-degree hybrid. Okay. We will be looking at this device, how to actually build this later on. But essentially, this is a kind of power splitter where if you send in a signal from port 1, it will split equally into port 3 and 4, but with the same phase. So, which means that if I send a voltage V, this will be plus V over root 2, and this will be plus V over root 2. Okay, so let me call it VE1. And this is what explicitly now it means to excite. Even if this is now connected to a coupled microstrip line, you're going to get exactly the same power and in phase. So remember, these are AC signals, right? So what do I mean by in phase? That if this is like this, then this will also exactly be like this in the same phase. Okay, that's what even mode excitation means. But if I send in a signal on port 2, I'm going to call that VO, then you're going to get VO over root 2 and minus VO. Okay, so this root 2, because we are writing in voltages, because it's a power splitter, so the power will be V square over 2 and V square over 2, which will add up to V square, which is basically the power on the inside. Okay. So this 180-degree hybrid, essentially you can think of this as a splitter, which either split in phase or it can give you an out of phase split. Okay, so that's what this 180-degree thing written here means. That going from 2 to 4, it will develop an additional 180-degree phase shift, and that's why it will be minus. Okay. So now you see that this actually allows me to excite the even and the odd modes in the same setup. Okay, how this device functions, we will look at that later, but let's assume this. It also has this other parameter, which is loss, which is basically to model in a real case that this object itself might absorb some power, in which case the power coming out are not going to be exactly half the power you put in. Okay, so now I can put the second port here. And what it means is that if I now measure the reflection coefficient from port 1, that would correspond to measuring the even mode reflection coefficient. If I measure the reflection coefficient from port 2, it will correspond to measuring the odd mode coefficient. Does that make sense? It's because that this object actually creates the right type of excitation. And conversely, what it also does, I guess I should elaborate that. So not only does it do the splitting in this way, what it also means is that if I have a signal coming in to this port, which is of this type, then this entire thing will come out of port 1. So if I send two in-phase signals which are identical, it will come out of port 1. If I send in two out-of-phase signals which are identical, it will come out of port 2. Okay, so this maintains the symmetry in both directions. So what it means is that it will provide an even mode excitation, but it will also take the even mode excitation and send it to the correct port. Okay, so this is very important, otherwise the reflection coefficient measurement doesn't make any sense. An alternate way of thinking about this is that if now, so this is for the reverse path, if I now have a signal V3 and a signal V4, which is being sent in to ports 3 and 4, then the signal on 1 will be proportional to V3 plus V4, and the signal on 2 will be proportional to V3 minus V4. Right? This is entirely self-consistent with before, because if V3 and V4 were identical and the same sign, then this V3 minus V4 term will go to 0 and only V3 plus V4 will be there. If they were exactly equal and opposite sign, then the V3 minus V4 will become add up, and the V3 plus V4 term will become 0. Okay. But in general, this is what it means for an even and odd mode excitation to be separated. So in the most general case, you can have V3 and V4. Now, all of this is assuming that there is some kind of phase relationship between V3 and V4. If V3 and V4 are completely independent signals, which means like they're like noise, two independent uncorrelated noise, then there won't really be any difference between what is coming out of here and what is coming out of here. It will just be noise, and they will just both be added in the same sort of way. Okay, so usually these devices, their special properties make sense only when there's already some correlated thing going on. And this conversion from even to odd mode and those kind of things can happen depending on the boundary condition. You might have excited on the even mode and signals go out here, but maybe you did something where this signal returned with a +1 gamma, but this one returned with a -1 gamma. And you have now turned an even mode excitation into an odd mode excitation. And now it's going to come out of somewhere else. So we can actually check some of these things now. Okay. So double check that the circuit is making sense. So 3 and 4 are the outputs of this 180-degree hybrid, and they go to ports 1 and 2, which we are measuring. Ports 3 and 4 are terminated with this value ZL. Now, in order for all of this to have the right type of correct impedance, I need to set everything to the same impedance value here. So just for keeping track of the things, I'm going to define the ZP, but I'm going to make it equal to ZL, and then put ZP here. And not only that, this 180-degree hybrid also has to be defined in the correct impedance framework. Otherwise, this will not work because we are using this trick to measure a non-50 ohm type of device so that the reflection coefficients all make sense. So I have to put here also ZP. Now let's see. I guess should open. Open here. Oh, this is measure EW. This disconnected? No.
I think
Oh, sorry.
you have to choose.
No. I was just in the wrong unit, and I was expecting something to be, negative dB or something. It's fine. It was just in magnitude, so it was close to 0, and I was thinking 0 dB. So it's like, oh, why is it reflecting so much? It's fine. Okay, so I'm going to add that measurement here in the same graph. So this is now schematic 1.1. And now I will not use this G odd G even because I've already done that. So I'm just going to use standard port parameters, S parameter, S11, MACdB. That is going to be the equivalent of the even mode reflection coefficient. And then S22 for the odd mode. So now look very carefully. The brown one is S11, which is, remember, this is port 1, which is the even mode excitation. And that is high. The red one, which is now on top of this pink one, is S22, which is the odd mode reflection coefficient. And that is nice and low. And it's exactly matching the odd mode impedance measurement for this schematic. Okay, why? Because the port values are set to match the odd mode impedance we had calculated from here. It's close to 40 ohms. And what this is telling you is that the two techniques of measurement are in fact exactly identical, right? Remember, the pink is the odd mode impedance of that coupled microstrip circuit, but set up as a G odd measurement, whereas the red one is set up using this 180-degree hybrid and exactly matches. Now, because in this schematic, there's only one port impedance and it's all the same, and we are measuring the even mode, but the parameters are set up to be odd mode, so it's not matching. So if I just now change that, okay, it's so confusing now. Wait a second. Let's get rid of this. I only have ZL. Yeah. Okay, so now if I take this higher, now the even and the odd mode things will become different, right? Because the same port doesn't match the even and the odd mode case. So now around 60 ohms, I'm getting the nice results. In fact, let's see for which one. So we should set this up to the same value. Okay, I guess now I know what this is, so it's fine. And I should change this to even, so that we can now see that they are also identical. So if I set both of them to the same values, now in the new setup, the matching condition, I mean, the port impedance are matched with the odd mode, even mode case. Okay, there's a lot going on. I hope it's clear. Maybe let me pause here and see if there are any questions on what I just showed here.
So again, this power splitter will only work if both 1 and 2 are connected to the same impedance port, right? We need to be careful.
You mean this?
Yes.
So we have, there might be slightly different configurations where it might still work, but we have actually taken a very extreme situation where the hybrid is defined with respect to a port impedance, like a port characteristic impedance value of ZP, and all the port impedances are also the same, right? This is the object we are studying. So that, that is whatever it is. But ZP and ZL are also the same. So this port impedance, the characteristic impedance of the directional, the 180-degree hybrid, and the termination impedance are all the same. And in this setup, they can either be 62.4 ohms or 41, which are two different numbers. So that's why we cannot get simultaneous match for both even and odd mode in this structure, because they are different. So we're just trying to set up a measurement so that you are able to see both of them by choosing the correct set of impedances.
Yes, I meant to ask that. Okay.
You're saying that this.
So let's say if we only want to measure the even mode, then we still have to match the port 2 with the impedance of the splitter to get the correct gamma.
Okay, good question. So in fact, let's see. I understand what you're asking, and that's actually a good point. And yes, okay. Now the setup we have done. So let me just to prevent confusion, let me get rid of the other one. So we are now only looking at the schematic and the even. So port 1, S11 is basically effectively the even mode gamma, and S22 is the odd mode gamma. The impedances have been set to match the even mode situation, which is why S11 is low and S22 is somewhat intermediate, right? Some power is thing. Okay. Now what Jay is asking is, if we were only interested in the even mode, then does this port 2 impedance matter? Okay. Now what that means is that if I want to look at that, then first of all, I should not be looking at port 2 reflection coefficient. I only should be looking at port 1 reflection coefficient, right? And that of course is fine. It's some low value here. What I can check, however, is instead of looking at port 2 reflection coefficient, I can see what is going into port 2 if I'm measuring on port 1, right? So I can look at S21. So this will tell me that while putting an excitation here, does any power leak into port 2? Let's see. So I've changed this from S22 to S21. Let me enable it again and plot it. And here it is. It's basically 0. Okay. This hybrid is, of course, an idealized device, has this property that when you send in power from 1, it will split it equally to 3 and 4, which means there is no other power left anywhere to go, right? So it will never send any power to port 2. So this is actually often called the isolated port for port 1. Similarly, for port 2, port 1 will be the isolated port, provided the boundary conditions on the other end are perfectly absorptive or maintain the symmetry of the kind of excitation you have provided. Okay, so if that is true, I can disconnect port 2, which if I'm only measuring port 1, and it will not make any difference to the reflection coefficient here. So let me freeze this so that we have, this is the reference. So remember, this is transmission into port 2, which is some very low value. I'm going to disconnect this here because I'm not expecting any power to come out of here. So it shouldn't matter what's connected. And I go back and I do this, and okay, it's basically now this transmission to port 2 has become very small. It's showing minus 800 dB, but essentially it's the same, right? So does this answer your question? If one is only working in even mode excitation space, then this does not matter. You can leave this disconnected because nothing is going to come out here. And similarly, we can do the reverse. I can now connect this up, set this back to S22, set that to S12, put this close to now the odd mode matching condition, about 41 ohms. Okay. And now you see that S12 is very small, S22 is also small, as showing the matched condition, and nothing is going on here. And I could freeze this, disconnect port 1, Basically, nothing happens. Okay. Jay, does this make sense?
Yeah, I mean, I wanted to. So let's say in this case, when we are sending an even mode signal, it is coming back as even mode, and therefore all the everything
Exactly.
is coming back to port 1. However, if there is some sort of a, mixing when the signal
Yes.
comes back,
Yes.
and then some of it goes to the port 2, and there's an open boundary condition there.
Then
So I
that
was
would be a mess.
Yeah.
So you don't want. So okay. There are some things in this example which are slightly complicated, somewhat unnecessarily, because the coupled microstrip line we have designed has some strange even and odd mode impedances. It's 60 and 40 ohms. So it's none of them is matched to our 50 ohm system. So because of that, I had to change all the reference ports to a different value, right? But in what is important is that if a signal is coming out of the other port, so if you have excited even and something is actually coming into the odd port, in order for that power to never re-enter, like not reflect, it should be connected to a matched load or a port, whatever is the characteristic impedance you are shooting. So here, since everything is ZP, then it is fine. It doesn't require it to be the specific even or odd mode case. Here, we are choosing two different parameters to understand two different situations, because we cannot match both even and odd mode at the same time. In a real situation, the hybrid will actually be a 50 ohm device, and your coupler will also be transformed to 50 ohms at the level of the ports. But at the level of the coupler, it will be something different. And that is again important, because a 4-port device, so this hybrid coupler could also just be something like a coupled microstrip line. It could be, it's not, but it could be. But you always want the ports to which you are connecting signals from outside to be always a 50 ohm reference. Otherwise, it will just become extremely complicated to use. Okay. When I discuss the coupled microstrip line based device, which is actually called a directional coupler, it will become clearer what I mean by that. So the outside reference is always going to be 50 ohms, and you just sort of design the device in such a way that when things are terminated properly, then everything works out correctly. I'll now give you an example of how mode conversion can actually happen. I had sort of hinted at it in an example just a little while ago, but I'll now explicitly show you what does this even odd mode mixing actually means. Okay, so let me make a new schematic. I'm going to use this hybrid. Okay. And let's make a new graph. I'm going to look at reflection. Basically, I guess all 4-port parameters. S11, S21, S12, and S22. Oh, sorry. So blue and red are the reflection coefficients, S11 and S22, and pink and brown are the transmission coefficients, S21, S22. Excuse me. So let's look at this again. 3 and 4 are unterminated, which means that any excitation which comes to 3 or 4 is going to get reflected. And what it's saying is that first thing, there is no transmission from 1 to 2 or 2 to 1. That's because the symmetry is maintained. And everything which goes in comes back. That's why you have a reflection coefficient of 0 dB on either the even mode or the odd mode. Okay. Now, these are open ends, right? So open ends means they reflect with unity reflection coefficient +1, and it's the same for both of them, right? If I put a short circuit, so connect to ground for both of them, again, it's the same, okay? In fact, I think to look at this carefully, I should change this not dB, but to, I think just do real part, because anyway, it's not. Okay, so reflection coefficient is 1, transmission coefficient is 0. I put short circuits. Reflection coefficient now is -1 and transmission coefficient is 0. Okay. I hope this makes sense. I've just flipped both of them to minus. So whatever happens, if it is an even mode excitation, it came as +V. Now it entered as -V, but that is still an even mode excitation. So it went back to 1 only and not to 2. Okay, but overall it developed a sine. So that's why I moved to real of the gamma so that you could see the sine flip going on here. However, if I now terminate one of them with an open and the other one with a short, and let's do it the other way around. Now the plus is going to go back as a +-. Okay, and see what happens to the plots here. It's looking exactly the same, but the colors have switched. Remember that blue, which was S11, is now 0. Red, which was S22, is now 0. But the transmissions have now become unity. And the reason is that now an even mode excitation is completely changed into an odd mode excitation. And an odd mode excitation is completely changed into an even mode excitation because of this sine flip. Okay, so that's how one can change even to odd mode excitation. These are, of course, idealized situations. You could do something else, for example, where you put a section of transmission line on one of them. Okay, let's make this 90 degrees at 6 gigahertz. What's going to happen? This wave on 3 is going to reflect with +1, but this wave on 4 is going to travel, accumulate a certain phase, and then come back with a different phase. And that phase will also be different for different frequencies because it's a fixed length of transmission line. So the phase accumulated will be different. And what you're going to see now here is even and odd mode getting mixed into each other depending on the frequency and the phase. But always the transmission and the reflection are similar, but they change together. Like the blue and the red are changing together because of this, the way I have defined this, and then the pink and the brown are changing together. So at 6 gigahertz, where it was 90 degrees, so but it is a round trip. 90 plus 90 is 180. So it caused a complete flip. So the even and the odd modes got, so the transmission, the reflection got changed. And then again, so it will periodically do this. So if you chose a longer length here, then this thing will happen, a lot faster in frequency space. You get many more such oscillations. Okay. So when working with these kind of matched or balanced networks related to coupled things, then these phases become important if you're worried about even and odd mode, because there's just the phase which determines whether something is an even mode or an odd mode excitation. So you have to keep, cable lengths and transmission lengths to be identical if you don't want any weird mode mixing to happen. Otherwise, you can get these kind of effects going on. Okay, so I think I will stop there. But this is somewhat subtle and complicated, but you'll get used to it as you think more and more about it. Are there any questions? No?
So in practice, if we make this couple strip lines, so they will always be like the even mode is 60 ohm characteristic impedance, and the odd mode will be 40 ohm.
No.
Like
I mean, that all depends on how you choose these parameters, right? So if I now change this to some different gap, then this changes, and correspondingly the odd mode changes as well. But it will, really depend on. So in fact, you see, there are some things where you cannot do even the gaps to be very small. But for a microstrip, I think you cannot make these very different from these values here. But for strip lines, you can. And that doesn't matter. They don't have to be 50 ohms, because most of the time they're used when there's some kind of interference effect is being exploited. So when I look at I will actually tell you which parts to read, which explains the device performance. And usually what that means is that you excite from, say, port 1, and the structure then means that it is, and remember, if you excite only from port 1, it means that you are exciting a combination of even and odd modes, right? Because essentially it's saying that you have put in V1 and V2 equal to 0. Now that is neither an even mode excitation nor an odd mode excitation, but you could then think of that as an even mode excitation of V1 plus 0 divided by 2 and an odd mode excitation of V1 minus 0 divided by 2. And then that will propagate through this system, experience any reflections or not on the other side, and give rise to either a reflected wave, which will again then come here and then, depending on the port impedances, transform. So that has to be set up correctly if you want this 4-port device to have a particular kind of response which you're trying to design. So this one device, which is commonly designed using this technique, is called a directional coupler. And a directional coupler is a 4-port device, and it has this property that if I send a signal on 1, a large fraction of that, something like 99% of the power, will end up in 3, right? And that actually seems to suggest that, oh, this is just basically a straight line, it's just going there. But 1% of the power goes to port 2, and 0% of the power goes to port 4, which is again called the isolated port. And it's perfectly symmetric. So similarly, if you send power in from 3, 99% will go to 1, 1% will go to 4, and 0% will go to 2. And again, fully symmetric. If you send it on 2, 99 will go to 4, 1% will go to 1, and 0% will go to 3, and similarly for 4 as well. Okay. This kind of a device, a directional coupler, is used for 2 different purposes. One is as a reference, like to create a tap of the signal which is flowing from 1 to 3, right? So there's some power going in from 1 to 3, and you want to actually know how much power is going, but you cannot put like a power meter inside without, disrupting the flow. You actually want the flow to be happening to wherever it's going, but you want to be able to get a sample of this. So you design a coupler which has a known coupling constant between 1 and 2, and then you put your measurement meter here. So that way it's like a little tap, a small voltage divider kind of thing, which doesn't affect the main signal so much, but you then get a reference. But you know that this power is only 1% of the total power. So you multiply that by a factor of 100 to get a sense for the true power flowing through this. And that is one application of this. The other application is actually to do a reflection measurement. And the way that works is that you send a signal on 2 that sends 1% of the power to 1. The 99% of the power goes to 4 is actually lost. You just put a 50 ohm termination here. But 1% of this power goes to 1. And on 1, you put your device, the one you're trying to measure. Okay. So that then goes to your device, reflects, and then 99% of that comes back out of this. So that way, the incident signal and the reflected signal have been separated. Okay. The price you pay, of course, is that only 1% of the power you put in gets used up, but that's okay. Usually you don't care about that. And in fact, these kind of direction couplers are central to measuring reflection coefficients in real instruments. That's actually how they separate out incoming and outgoing waves. It's a little bit more complicated than that. And I will discuss that towards the end, maybe like in another 2 weeks or so, this whole network analysis measurement. Okay. So, but in order for that property, these set of properties, which I explained, that if I send a signal on 1, 99 should go here, 1% should go here, and 0% requires some conditions to be satisfied for the length of the coupler, the even and the odd mode impedance of the coupler. And that's what is, described in this, when you look at the math behind the coupler design. Okay. So just any coupled transmission line of this type will not work or will not do the job you're trying to. You have to choose the parameters correctly. Okay, and it is also matched to 50 ohms on all the ports. So which means that if all the ports are terminated by 50 ohms, then that fourth port will also not show any reflection. And again, remember that many of these properties are often idealized properties and will typically only be satisfied for one frequency perfectly, but it will be satisfied for a reasonable number of frequencies over which is designed to work. And that depends on the design. This is the simplest type of direction coupler one can make, but there are many more other designs where you can improve upon this, give more bandwidth. So we had discussed that, in the context of the impedance transformer, that it only also works only at one frequency, but then you define a range of operation. So what does it mean that it won't work? It just means that the coupling factor might not be 1% uniformly. It might vary a little bit. The isolation might not be 0. So some power will leak out of 4, but it will still be small. So those things will determine the performance of the device.
Okay.
Okay, any other questions? Okay, all right. So then I guess, yeah, we will meet tomorrow. Okay, see you then.